So today I'll be taking one extra class, and in this extra class, I'll be discussing some of the topics which I was unable to discuss in the previous classes. Okay. So one such topic, I'm writing down all the topics first of all. So let me write down in the slides all the topics. Okay. So we will be discussing universal motor. Then we will also discuss field test. Like how we do Hopkinson's test and Swinburne's test, there is something called as field test. Field test on DC motor. And then we will also discuss DC motor electrical braking. So these are the three things which we will try to cover in this class. Okay. So let us start with the universal motor. Now you see, so let us first write, if suppose I have a shunt motor, okay. So let us suppose I have a shunt motor. So shunt motor is something like this. This is the field winding. Then this is the armature with its armature winding. Let us suppose the armature winding is here. So field winding is having field resistance RF, armature winding resistance having RA. Okay. Now let us suppose I give it a supply like this, positive, negative. So we know what is the expression of electromagnetic torque. Electromagnetic torque expression we have derived. So how we have derived? We have derived it from electromagnetic power developed by omega. So you will see that there will be some proportionality constant. Let us say it is K. And then it will be dependent on phi and Ia. K phi Ia. Okay. So torque is proportional to IF and proportional to Ia. Okay. So let us say that the direction of IF is like this and direction of Ia is like this. Okay. So let me draw the direction more clearly. Okay. Now let us say that this DC shunt motor, we now give it a negative supply. Okay. So in that case, you will see that the IF and IA direction will no longer be like this. It will be in the opposite direction. Okay. So IF will also become positive, opposite, and IA will also become opposite. So in this case, torque is also proportional to minus IF, because compared to the previous direction, it is in the opposite, right? So minus Ia. So what about the torque? Torque is still positive. Okay. So even when we reverse the supply voltage, the electromagnetic torque produced is in the same direction. So we can think that, okay, let us connect what you say, AC supply to a shunt motor. So let us suppose say we are connecting an AC supply to a shunt motor like this. This is motor armature. So what will happen when this is positive? So your current will be like this. And when it is negative, the current will be in the reverse way. But we think that electromagnetic torque will be still IF, IA, positive direction. But there is one catch. Now what happens that this armature inductance is very low. Whereas this field inductance, this understand this, we are talking for the shunt machine, okay, not for series, for shunt, okay. So field inductance of shunt machine is very high. So, Sambit, I was discussing was, I was discussing what you say, some of the things which I was unable to discuss. Okay. So, I was trying to discuss the universal motor, field test on the DC motor, and DC motor electrical braking. Okay. This class will not be a long class. This will be only a 1 hour class, or maybe even less than that, 45 minutes to 1 hour. Okay. In that, I'll be discussing some of the things which I was unable to discuss. So from this, there can be some theory questions. Okay, that is why I'm discussing this. That what is a universal motor? Okay, and what is the field test? Like if how we do Swinburne's and Hopkinson's test, that there can be some question on field test. Okay, okay. So how to see that, and then there is DC motor electrical braking. Okay, so I'll be discussing these things because there can be some theory questions on this. Okay, so here as I was saying, in a if you see in a shunt motor, so I have drawn a shunt motor here. Okay, so it is having a field winding, it is having an armature winding, and this is the motor. Okay, so we know that what is the electromagnetic torque? Electromagnetic torque developed is electromagnetic power developed by omega, and we know that what is the electromagnetic power developed? It is EB into IA by omega. Remember that diagram that here we had first of all V into IL, then we had copper losses, then we had EBIA, then we had rotational loss, okay, and then we had what you say, your shaft power, okay. So here this EB into IA is electromagnetic power developed, okay. So from this electromagnetic power developed by omega, we get electromagnetic torque developed, okay. So you will see that the electromagnetic torque is proportional to product of IF and IA. Okay. So as I was saying that if I give it suppose a positive supply like this, suppose I give a positive V supply like this. So what happens? The IF is in the downward direction and IA is like this. So you will see that the torque is IF and IA. Let us suppose the downward direction we are taking as positive direction, and this IA, this downward direction also I am taking as positive direction. So IF and IA both are positive. So torque is also positive. Okay. Now let us suppose I give it a negative V supply. Instead of giving it a positive V supply, I have given it a negative V supply. So what happens? So since I have given it a negative V supply, so what will happen is field current will flow in this way and armature current will flow in this way. Okay. So torque developed is what? I minus IF into minus IA, क्योंकि if I have taken downward direction as positive for both, then upward direction means negative currents. So IF is with negative sign for direction and IA is with a negative sign for its upward direction. So what happens? Negative negative cancel out, it becomes positive only. So this torque is also in the same direction. So I wrote that even when we reverse the supply voltage from positive to negative, the electromagnetic torque produced is in the same direction. So we can think that, okay, instead of supplying it with a DC supply, we can give it an AC supply to this motor. Okay, so because we are getting because the purpose of the motor is to provide electromagnetic torque in one direction and it is providing the electromagnetic torque in one specific direction. Okay, so we can think that, okay, let me give it a AC voltage. So even if it is a positive voltage, then it will torque will be in the one direction. And if in the AC supply we get negative voltage on its own, because AC supply we have positive and negative like this, right? So we do not need to like continuously change. It will automatically change the direction of voltage supply. Okay, so in that way your my IF and IA will be negative in that negative direction case, but the torques will be still produced in the positive direction. Okay, but there is one catch, as I was discussing, that why you cannot do that with the shunt motor. Okay, you can do that with the series motor, but why you cannot do with the shunt motor, I was discussing that. Okay, so here if you see, so armature inductance for the shunt machine when compared to the field inductance is very low, and field inductance of this shunt machine is very high when compared to armature inductance. Okay, so what happens? So let me draw the phasor diagram. So here, let us suppose the voltage V is in this direction. Okay, so let us suppose the voltage supply V is in this direction, AC. Now, what about IA? Because I said that armature inductance is very low and can be neglected. हाँ, tell me. इ- इसमें न्यूमेरिकल क्वेश्चंस नहीं आएगा, पर थ्योरी क्वेश्चंस तो कहीं से भी आ सकता है ना। मैंने टॉपिक डिस्कस नहीं किया था, तो मैं इसलिए डिस्कस कर रही हूँ। क्या बोल रहे हो? हाँ बोलो।
मेरे तरफ से कुछ साउंड आ रहा है क्या? मैं थोड़ा ट्रैफिक में थोड़ा हूँ, जा रहा हूँ ना, कॉलेज जा रहा हूँ, तो कुछ साउंड आ रहा है क्या मेरे तरफ? मैं थोड़ा माफ।
हाँ, थोड़ा थोड़ा साउंड आ रहा है, ठीक है। तो अगर तुमको कुछ, हाँ हाँ, तुमको कुछ पूछना होगा, यस यस, हाँ, यस 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 यस, ठीक है। ओके ओके। So now, as I was discussing that the VAC supply is in this direction, let us suppose this is our voltage phasor. Okay. Now what will happen to IA? Because armature inductance is very low, so we can say that the armature inductance when compared to armature resistance is very low, so we can neglect armature inductance. So we are assuming that there is only armature resistance here. So because it is resistance and we know that the voltage and current for a resistance are in phase, so let us suppose IA is in phase with voltage. So this is how I have done it, by neglecting armature inductance. Okay. But what about the field inductance? Field inductance is very large. Okay. Field inductance is very large. So what happens is that uh, field inductance is much larger compared to field resistance. So we can take that, okay, field is inductive in nature. So since field is inductive in nature, so what happens is that the field current, because for an inductance, what happens? For an inductance, the current lags the voltage by 90 degree. So IF is lagging the voltage V by 90 degree. Okay, because it is inductive in nature. ठीक है, इंडक्टिव इन नेचर। फील्ड इज इंडक्टिव इन नेचर, ठीक है। सो यू कैन सी व्हाट इज हैपनिंग टू आई ए एंड आई एफ। सो इफ आई ड्रॉ द देयर instantaneous voltage waveforms, instantaneous current and voltage. So here this is, let us suppose IA. So IA is in phase with V. Now what about IF? IF is lagging IA or V by 90 degree. So IF is something here. Okay. So this is IF. Now what happens is, like, we can see that we can divide these waveforms in these segments. Okay, so this is these four segments. Okay, so this whole 360 degree we can divide it in the four segments. Now what are these four segments? So let us say this is segment 1. So in this segment, IA is positive. So IA is positive, but IF is negative. Okay, so IA and IF product torque is IF and IA product. So this torque becomes negative in this section. Okay, then in the next section, IA is positive, IF is also positive. So torque is positive in this section. Okay, so I'm writing the torque down. Torque is negative, torque is positive. Now in this section, IF is positive, but IA is negative. So IF and IA product is negative, which is torque is negative. Now both IF and IA are negative. So here torque is positive. So you can see that torque is a kind of sinusoid. Okay. So since this torque is kind of sinusoid, so what happens is that the what you say the average torque, electromagnetic torque becomes almost zero. Okay. So for a shunt machine, what happens is that the average electromagnetic torque is zero. Okay. So that is why you will see that we will go to series machine in which the IA and IF are in phase. Okay. So you will see that in the series machine, IA and IF are in phase. So here for the series motor, so for a series motor, if I draw, so this is the supply. Let us suppose we are giving it a sinusoid supply. Here there is the field winding, there is the armature winding. Okay, like this. So this is IF, this is IA. Okay. So again, similarly, if I draw what you say the um, phasors of IA and IF and IA, where this not phasors, basically the instantaneous waveforms. Okay. So let me draw then. So this is IA and this is IF. Okay. So let us say this is, so you can say, see that IF and IA are same. So here this is, let us say this is IA. So IF is also same. Okay. So on top of it only is IF. So what happens is that the torque IF and IA is always positive. Okay. So that is why a universal motor is a series motor. Okay. So a universal motor is a series motor. Okay. But you will see that its efficiency is poorer. Okay. Compared to normal DC machine, its efficiency is poorer. Now, why that is because if you see here, if I draw this, so let us suppose I'm drawing the poles. Okay. Now here what is happening is that we are giving, because let us say this is your stator. Now we know that in the armature there is armature winding. Now in the stator previously we were giving it a DC what you say supply, so that the DC flux is generated. Okay, so previously the flux which was generated, okay, it was DC. But now what is happening is that the flux which is now being generated is AC. So before it was a DC flux means it was a constant flux like this, flux DC. But now since we have given it an AC supply, okay, so the flux which is flowing in the stator is phi AC. Okay, so there is phi AC means there is a so now previously in the stator the eddy current and this what you say this core losses hysteresis and eddy current losses were less. Okay, in the case of DC. So when DC supply was given, eddy current and hysteresis losses was very less in stator. Now these eddy current and hysteresis losses increase in stator with AC supply. So, for the DC supply, which is the normal DC motor, so for normal DC motor, no laminations on stator. However, universal motor, which is DC motor with AC supply, laminations have to be there on the stator. Okay. So that is the case. Now we will see the what you say other things. Okay, so so this is the universal motor. Okay, so universal motor is what? It is a series motor which is given an AC supply. 1 second. हेलो. मैं बाद में बात करती हूँ, ठीक है, मेरा अभी वो है क्लास क्लास, ठीक है. हाँ, बाय. So this is the series motor. Now series motor means that here basically you were giving the universal motor is series motor with an AC supply. Now because you are giving an AC supply, so the field which is the flux which is produced is time varying in nature. Before it was a constant flux, okay, but now it is time varying flux. Now whenever you are giving a time varying flux, so eddy current and hysteresis loss increase in the stator, and hence you need laminations. So there may be questions that okay, in universal motor what is the nature of flux, or is in universal motor is there laminations of the stator, laminations on rotor, or laminations on both stator and rotor? These kind of theoretical questions can come. Okay, that is why I'm discussing this topic now. And why a shunt machine cannot be used as a universal motor? What is the problem? So you can say that the average electromagnetic torque is 0. Okay, now we will see what you say field test on the series motor. Okay, so for here, so let me draw it freshly so that you can see it here. Okay, so let me do this. So this is field test on series motor. Okay, so it is like Swinburne's and Hopkinson's test. Basically what we do is we try to find out basically the what you say efficiency of the machine. Okay, so here what we have is we have a first of all a series motor. Okay, so series motor means what? It has its field winding, so basically field winding RF, then armature winding. So let us say it is RF motor, this is RA motor. Okay, so this is the thing. Now here let us suppose we have a shunt generator, DC shunt generator. Okay, so DC shunt generator like this, and then its field winding is connected in series with this motor. Okay, so this is RFG. array. And then you have RFM. Okay. So RFG and then RAG. And this is the external resistance which you have put. Let us say this is R load. Okay. You are giving it a V supply. Now, this motor and generator, they are mechanically coupled. Motor and generator are mechanically coupled. Now, what happens is that since you have given it a voltage supply, so what happens? There is some current which is flowing. This is, let us suppose this current is I, not I2. Let us suppose this current is I. Okay. So because you are supplying the motor, so it is drawing the current I. So what will happen? The motor will start rotating. Another thing to note is that because this is a DC series motor, you cannot start it. We have discussed that you cannot start a DC series motor with no load. The load for this DC series motor is the generator. Okay, so generator is acting as the load. We are not starting this motor without any load. Okay, so the generator is the load. Now what happens that because you give it you give it the voltage and current, so you give it a voltage supply, so current starts flowing. Now so here what, and because it is having the flux also, so it will start rotating. Okay, let us suppose it is rotating with a speed n. So because this motor and generator are mechanically coupled, so this generator also starts to rotate with the speed n. Okay, and because this here you have the speed n, and because there is current I which is also flowing in the field current of the generator, so there is flux and then there is speed. So what happens in the generator? You have back EMF EB. Okay, so so you have a back EMF in the generator developed. Back EMF means basically generator EMF EG. Okay, so EG is the generator EMF. Now because of this EG, there is some current I which is flowing, okay, in the load. So because of this EG into I, there is an electromagnetic torque. So this electromagnetic torque is opposing the speed. Okay, so this is basically the load torque. So electromagnetic torque of the generator is the load torque. Okay, so this is the load torque. It is opposing, you see, the direction of speed. So speed is in this direction, but okay, so this is but it has to be in the opposite direction. Okay, so this is opposing the speed. But for this case, this electromagnetic torque due to the motor is in the same direction of the speed, because that is the torque which is driving both of them in the to rotate in this direction with the speed n. Okay, so now what is the input? So input is V supply into I. So this is your input. Okay, so this is the input, and what about the output? So output here is this Eg into I. Okay, so now what about losses? So let us say copper loss on motor. So copper loss in motor is copper loss in the field winding of the motor. So field winding of the motor is having current I square into the field resistance. So this is RFM plus copper loss in the armature of the motor. So let us say this is I square, which is the current flowing in the armature. This is the same current into RAM. Now what about copper loss in generator? So in the field of the generator, you have current I. Okay, so this is I square RFG. So copper loss in the field is I square, which is the same as the current in the motor. So I square, and the field resistance of the generator is RFG plus, let us say this is load current IL. So this is EG into IL. Okay, so IL is the load current. So here armature is the load current is flowing in the armature winding of the generator. So this is IL square RAG. Okay, so we know that input is equal to output plus losses. Okay. So what is losses? Losses is output minus input. Okay. So what is the output? Output is Eg into IL minus input is V supply into I. Okay. And what are these losses? These losses are all the losses. Okay. All losses. So all losses means copper loss of motor plus copper loss in generator plus rotational losses. Okay. So this is equal to I square RFM plus I square RAM plus I square RFG plus IL square RAG plus the rotational loss. Okay. So let us suppose the rotational loss is plus R. Okay. This sum is equal to Eg into IL minus V supply into I. So from this equation, you can find out the rotational loss R. But this rotational loss R is the rotational loss of both the machines combined. Okay. So individual machines, the rotational loss will be R by 2. Okay. So this is exactly like how we do the in Swinburne's test and Hopkinson's test. When we do no load test to find out the rotational loss, it is the same way. Okay. Here we are finding the rotational loss. And then we can use this rotational loss in efficiency calculation. Okay, so let you see here. So in the SIR's lecture also, lecture 92, if you see, he has basically done the same thing. Okay, so here also he is finding the total copper loss, and then from the total losses, which is equal to the total ohmic loss plus rotational loss of both the machines. So he from there he is finding the rotational loss of both the machines. Like this only exactly he is finding. So here also this R is the rotational loss of both the machines. Okay, so let me write that R is the rotational loss of both the machines. Okay, so that is how the rotational loss of both the machines was obtained, and then half of the rotational loss is assigned to each of the machines. Okay, so here also R by 2 is, or W naught by 2 is the rotational loss of individual machine. Okay, now we will see how to do the efficiency calculation. Now for calculating efficiency of motor, okay, so for calculating efficiency of motor, what is done is that you connect a voltmeter such that the voltmeter is connected across the field winding of the motor and armature winding of the motor, like across this armature and field. So it will, let us suppose it is measuring voltage Vm, because the supply voltage is applied across the field winding, armature winding of the motor and field winding of the generator. But if you're trying to find the efficiency of motor and efficiency of generator, so this V into I is total power input for power input for motor as well as power input for the field winding of the generator. But we want to only find the power input of the motor. So that is why we have connected a voltmeter so that we can measure this Vm across the motor. So power input to the motor becomes Vm into I. Okay, so we know that efficiency is output by input. So Vm into I is the input minus the losses. Okay, so minus I square RFM RFM is the VMI is the input of the motor minus the copper losses in the field winding of the motor minus copper loss in the armature winding of the motor minus R by 2 or W naught by 2, where W naught was the total rotational losses of both the machines, which we have found using this. Okay, so from this calculation we have found rotational loss of both the machines, and now we are using the rotational loss in individual machine, this value, in the efficiency calculation. Okay, similarly for calculating efficiency of the generator, so what we have done, that in the generator the voltage across this generator is, let us suppose, V2. Okay. V2 is the, what you say, generator voltage which is being developed. Okay. So V2 into IL is the output. Now what about the, so here this is output by input, and we know that here output is nothing but input minus losses for the case of motor, and for the generator input is output plus losses. Okay, so here for calculating efficiency of generator, you are basically adding the copper loss in the generator and then rotational loss of the generator. Okay, so that you can calculate the efficiency. This is another, what you say, method, like how we do Swinburne's test and Hopkinson's test. It is another method. Okay, so some question may come from this, so that is why I've discussed this field test on series motor also. Okay, now another thing is that what is the condition of maximum efficiency? Okay, so what is the condition of maximum efficiency? If you remember that I have discussed that the condition for maximum efficiency is that when the variable loss is equal to the constant losses. Okay, so let us derive that. So how to derive that? Let us see. Okay, so what is the condition for maximum efficiency? We know that variable loss is in this shunt machine. So for shunt machine, if you see, what about the if you see the field losses is constant, because as long as this terminal voltage is constant, V is constant. Okay, so your V by RF, or V by RF will give you field current, so that I field current will remain constant. So field current will remain constant means that field current square into RF will also remain constant. Okay, so so basically the variable loss consists of copper loss in the armature, because IA will vary as your load varies. Okay, so as your load varies, so the IA current which is getting drawn by the motor will vary, and hence your copper loss in the armature will vary. That is why the variable loss in the shunt motor is only the armature copper loss. Okay, not the field copper loss. Field is constant. As long as this terminal voltage is constant, your field is constant. Okay, so this is IA square RA. Now, what is the efficiency of the motor? Efficiency of the motor is input minus all the losses divided by input. Now, input is V into this IL. Okay, load current. So, V into IL is the input, minus V into IF is the, what you say, loss in the field winding. So, V into IF is loss in the field winding, minus I square RA is the loss in the copper loss in the armature winding, and then you have rotational losses. So from the input, we are subtracting all the losses to get output. Tell me. हाँ, देखो ये output by, see, this is output by input only ना. Now what is output? Output is input minus losses. So here we are writing output as input minus losses. So input is V into IL minus losses, तो जितने भी loss है minus all the copper losses minus rotational loss. So all the copper losses means IA square RA copper loss in armature. This is IF square RF. Okay, this is same as IF square RF. Okay, this is IF square RF, and this is rotational loss. So all the losses we are subtracting from the input to get output. Hello, is it clear? ठीक है, ये भी तो वैसे ही लिखा है, पहले भी तो ऐसे ही लिखा था, यहाँ पे भी तो आउट, जब हम लोग एफिशिएंसी ऑफ मोटर लिख रहे थे इन द फील्ड टेस्ट ऑफ एफिशिएंसी, वी रोट इट एज आउटपुट बाय इनपुट ओनली, वेयर आउटपुट इज इनपुट माइनस लॉसेस. तो मोटर का इनपुट यहाँ पे बीएम इंटू आई है, माइनस ऑल द लॉसेस ऑफ द मोटर विल गिव मी द आउटपुट. ठीक है, और क्योंकि जैसे जैसे मैंने पहले बताया था ना कि जनरली मोटर में मोटर का इनपुट क्या है? इनपुट इज इलेक्ट्रिकल. ठीक है, सो वी कैन एक्सप्रेस द एफिशिएंसी इन टर्म्स ऑफ इलेक्ट्रिकल क्वांटिटीज. ठीक है, सो बिकॉज इट इज बिकॉज मोटर का इनपुट क्वांटिटी इज इलेक्ट्रिकल, सो वी राइट इट एज इनपुट एंड आउटपुट बाय इनपुट. ना आउटपुट वी एक्सप्रेस इट इन टर्म्स ऑफ इलेक्ट्रिकल क्वांटिटी. Okay, so output become input minus losses by input for motor. Now what about generator? Generator ka output is electrical. Okay, so efficiency of generator is output by input. ठीक है. Now output is electrical, so we let it be. Now input we write it as output plus losses. Okay, this is generally what we do. Okay, for efficiency of generator, because output is electrical, so we express it in terms of output quantity. And here efficiency of motor, because input is electrical, so we express efficiency of motor in terms of input quantities. Okay, so that is why I have written it as input minus losses for motor. Okay, like this. Now here, so here you see, this is so we are assuming that this armature current is very large compared to field current, which is generally the case. Also you will see that the armature current is like 20-25 ampere, whereas the field current is like 1 ampere, sometimes 0.5 ampere. Okay, so that is why armature what you say, VIF is neglected. Okay, so VIF is like neglected, and IL is approximately thought to be same as IA, because IL is IA plus IF, but IF is very small compared to IA, so that is why IL is almost equal to IA. Okay, so this becomes VIA minus IA square RA minus rotational losses divided by VIL. Okay, now here it is written in more simplified manner. So here the fractions are separated. Then here, because VIA and IL is almost equal to IA, so VIA becomes 1. Then minus IA square RA, and in place of IL, you write IA. So IA gets cancelled. It becomes IARA by V minus protection losses by VIA. So it becomes 1 minus RAIA by V minus protection losses by VIA. So in this whole expression, I am just replacing IL with IA. That is all. Okay. So in this whole expression, I am replacing IL with IA, and here I have neglected IF. Neglected IF. Okay. So, so for finding out the efficiency, what we will need to do is, we need to find the value of armature current for this efficiency is maximum. So what we do, we know that for getting, for what is the maximum, what is the condition of maxima, that efficiency with respect to armature current, for the value of armature current, because we want to find at which maximum efficiency is there. So this derivative is 0 for maxima condition, maxima or minima, but here we have maxima, so we are doing it derivative at 0. Okay, so here what you will get, so if I do derivative of this, so the derivative of this with respect to armature current becomes minus RA by V, because IA का derivative क्या आएगा, IA के with respect में, तो IA का derivative becomes 1 with respect to IA, so this becomes minus RA by V minus protection, this P rotational by, this is what, minus 1 by IA. So what is the derivative of minus 1 by x? It is what you say, plus 1 by x square minus because 1 by x ka derivative kya hai? Minus 1 by x square. But here there is already another 1 minus sign. So this minus will become plus. So this becomes VIA square. Okay, so this is 0. So this derivative is 0. So PV also you can cross multiply to 0. So if you simplify, so if you simplify this, if you cross multiply and take the take it to proper position, you will get this. Okay, so you will get this IA square. So this rotational losses is equal to your variable loss. Okay, IA square RA loss, which is the approximate condition of maximum. Okay, so for maximum efficiency, if I would have not neglected this IF, you would have seen that this IA square RA, so then you would have seen that IA square RA is equal to rotational loss plus VIF. Okay, this is approximate, this is exact. Okay. So this is the exact condition of maximum efficiency where the variable losses is equal to the total constant loss. Now here the constant loss consists of VIF also. That is why I have included plus VIF. Okay. But here we have derived IS square RA is equal to P rotational because here we neglected IF everywhere. If we would have not neglected VIF everywhere, then you would have seen that we would have gotten this. Okay. This exact expression. Okay. If we do not neglect IF, you can try it. Like after maybe your exam, if you want to see that whether it is actually true, then you can try it. Okay. Now, let us see there is something called as electrical braking. Okay. So you see, because your DC machine, so it is something like this, that once you have um, started your DC machine, so let us say this is the field winding and this is your shunt motor. Now, once you have started to rotate this shunt motor, okay. So this is rotating. Let us say this is rotating with speed omega. Okay. And this is the field current, this is the armature current. Now what happens, like if suppose you want to stop your DC machine, so let us suppose you have removed the voltage supply. Now since you have removed the voltage supply, so what happens is that the field winding IF is equal to residual flux because this flux will now no longer be getting supplied by the DC voltage supply. It will be equal to residual value. Okay, this flux. Now what about this omega, because it is rotating. Okay, it is rotating with in one particular direction, so it is having some kinetic energy, half j omega square. So it is having some kinetic energy. So it will take, depending on how much is your inertia J, it will take, if it is a very big motor, then it will take like even seconds for this motor to stop rotating, right? So if suppose you want to stop this rotation of motor quickly, then what you do some things, something known as braking. Okay. So something known as electrical braking. So how to do it? There can be mechanical braking also. Mechanical braking means you are applying some shoe kind of arrangement which basically gives more friction to the motor. But generally what happens is that in that method there is lot of friction losses, and also what may happen is that your motor will experience wear and tear. Okay, so that is why we do not generally prefer mechanical braking. Okay, we generally prefer electrical braking methods. So here these are some of the electrical braking methods. So we will be discussing dynamic braking and plugging. Okay. Now here, if you see in the dynamic braking, basically what we do that we have a this three switches kind of arrangement. Like, so this is, let us suppose you have switch like this. Now you can, so initially when you were running your motor, your switch was closed in this position. Okay. So the motor was supplied with a DC voltage like this, and then it was rotating. Now, if suppose you want to stop the rotation of your motor, so how you will stop it? Okay. So to stop it, what you will do, you will move it in this direction. Okay. So you will move in this direction. So once now you have connected it in this direction, now here what you have, this is called as dynamic braking. Okay, this method which I am discussing. So here what you have is that here you have connected an external resistance R value. So because here your flux is still there. Okay, so flux is still there because this flux is still connected. So what is happening to IA? So initially IA was in this direction. Okay, flowing like this. So IA in the circuit was flowing like this normally. Okay, this is normal. Now with this regenerative braking, means dynamic braking, not regenerative, dynamic braking, what happens is this IA. Okay, so let us say this is IA motor, which is IA negative. Now let us say this is IA positive. Now here what happens, that here there is some back EMF because you are having flux, and there is some rotation also. Rotation because omega of the motor will not suddenly become zero, right? Omega is there because of the inertia of the machine. There is some omega. So before you want to stop this motor, let us suppose the speed at that point is n0 or omega. Okay, n0 or omega 0 is the speed. So what is the back EMF? So EB 0 is K phi N 0. Okay, K phi N 0 will be EB 0 because here you have phi, which is because this field circuit is still connected to this voltage, and here you are having the speed because speed cannot suddenly become zero. We want to make it decrease. So but before changing the position of the switch, let us suppose the speed was omega 0. So because of that there will be some back EMF. Now what is the current? Ia plus. So Ia plus is this back EMF divided by the total resistance. Now total resistance is this armature resistance plus this R external, okay, which you have connected for braking. So you see, IA was previously for motoring action like this, but right now IA direction has become like this. So IA direction have reversed. So you see, previously your torque was proportional to phi into IA negative. So it was in this direction. Let us suppose this is a negative direction. Okay. Now here torque is proportional to phi into IA plus. Now IA plus direction is opposite. This is positive direction. So let us say this is positive direction of torque. So what is happening, that the electromagnetic torque which is produced is now opposite in the direction, and this direction is opposing the speed n0. Okay, so this n0 is like this. So this TE plus, so TE plus due to the braking action is in the opposite direction. So it is opposing the speed. So what will happen, that if suppose you were doing it like this, that you just remove the voltage supply, so the time in which the omega will become 0, that time has now reduced, because at this point of time your electromagnetic torque was like almost 0. Okay, so it was almost 0. But here the electromagnetic torque is not almost 0, it is positive. Okay, so now पॉजिटिव मीन्स इट इज जनरेशन एक्शन. बेसिकली यहाँ पे क्या हो रहा है, बैक ईएमएफ जनरेट हो रहा है और इससे क्या हो रहा है, कहीं एनर्जी डिसिपेट हो रहा है. तो नॉर्मली यहाँ पे क्या हो रहा था, वी वर ओनली गेटिंग द फ्रिक्शन और द आयरन लॉसेस विच वर अपोजिंग दिस स्पीड. बट हियर वी हैव this the thing the torque another torque which is opposing the speed, which is this electromagnetic torque plus due to this action. Okay, so here the speed, the rate of decrease of speed will be more. Now if you want even more rate of decrease of speed, so we go to another method which is called as plugging. Now in plugging what we do, so in plugging, we basically connect along with this R external a voltage supply in this direction. Okay, so because it is in this direction, so what happens that when we want to close, when we want to stop this motor from rotating, so we move in this the switch from there to here. Now once the switch is closed here, so you will see that this back EMF which is generated, EB, gets added up with this V supply. So IA plus magnitude is much like even more. So this electromagnetic torque, which is K phi IA plus, is even higher. Okay, compared to the previous case. In the previous case, IA plus was nothing but back EMF by R plus RA. But right now, IA plus is back EMF plus V supply, which you are giving for the braking action. Okay, divided by RA plus RA. So here the magnitude of armature current IA plus, magnitude of IA plus is even higher. Okay. So because of this, the electromagnetic torque which is opposing the speed is even higher. Okay. So in this way, your machine will stop rotating even faster compared to this dynamic braking. Okay, so these are the braking methods. Regenerative braking sir has not discussed, so maybe that will not come in the exam, but this is the two braking which he has discussed. Okay, dynamic braking and plugging. Okay, so that is all for this class. So is there any doubt, Sambit? So if agar koi doubt, if you do not have any doubt, so I am stopping the class here. Okay, So I will be uploading this video and uploading these slides, so you can go through it. These are some theory which I did not discuss at the time. So there is this field test. So in the field test you can get maybe like in how in Swinburne's test and Hopkinson's test sometimes you get numerical. So you may get some numerical in field test also. Okay, so that is why I discussed this. But in other things there are mostly what you say your uh, theory questions. Maybe some one or two numericals can come on braking. Very simple will come, like you have to find this armature current, what is the new armature current for braking, if V supply is like this, it is plugging. So for writing those equations you need to know this theory, right? That is why I discussed this. Okay, so that is all for today's class. So I'm stopping the class here today. Okay, so then I'm stopping the class here today. So then thank you. Okay, so that is all. If there is no doubt, then I'm stopping the class. Okay. तो हाँ, सो ये है कि यहाँ पे हो सकता है कि मतलब देर कैन बी सम स्मॉल न्यूमेरिकल्स इन ब्रेकिंग, बट यू इन ऑर्डर टू राइट दोज इक्वेशंस you need to know na what is the braking, so how to write. So here it is only the back EMF by so in this case it is for this dynamic braking it is only back EMF by R plus RA, but here it is back EMF plus V external supply by RA plus R. Similarly this field test also there are some equations. So some, if numerical has to come it can come from this also, but other topics like universal motor and all, only theory questions can come from this. Okay, so that is all. So I'm stopping the class here today. Okay, ठीक है then. हाँ, all the best then. Okay, okay then I'm stopping the class. ठीक है, चलो, all the best. Okay, okay. हाँ, okay, okay.